So we've reached the point in the process where we have processed and assembled our hydrological and ecological data. We've joined it all together and we've done some initial data exploration to confirm that the data is suitable for calibrating a predictive model. In this tutorial, we're going to look at how we can then, within R, fit a linear mixed effects model and interpret the outputs from that model. There are already a number of well-established packages out there in the R user community for doing this. So in this tutorial, we're not going to be focusing on the HE Toolkit itself, but looking at how we can use these other packages to build models. It's important to be aware that there are at least two commonly used packages for fitting linear mixed effects models. The main one that we use is the LME4 package, and we use the LMER function from that package. This yields models with a model class of LMER mod. The LME4 package is a dependency of the HE Toolkit, so it's automatically installed for you when you install the HE Toolkit. And these types of models are also supported by some of the downstream functions, which we'll be looking at a little bit later, which allow us to validate the quality of our model. However, it's worth being aware that the same function can also be used from the LMER test package. The only difference, or the main difference, is that this alternative variant of a function gives us approximate p-values for the individual fixed effects in our model. These p-values can be useful as a guide to which variables of our model are more important. However, they are very approximate, I would stress that word, and they should be used with a pinch of salt and not used specifically to guide model selection. More on that a little bit later. For the next couple of slides here, I've got a couple of very simple examples to just illustrate the code that we can use to fit a linear mixed effects model. This first model, which we're calling Model 1, is the very simplest kind of mixed effects model. It's a random intercept model with a common slope. Here you can see that we are using the LMER function, and when we set up a model formula to define which variables we want to include as predictors. So we start off with our response variable, which in this example is a life OE ratio, so we're analysing macroinvertebrate data. Next we have the fixed effects. These describe the common slopes which apply to all sites. So here we've got just one flow variable, a standardised Q95 statistic. And then following that, within brackets, we have the site-specific effects. Here we have the biology site ID as our random grouping factor. So this identifies the fact that our data have a hierarchical structure and that samples are nested within sites. And the 1 before the bar tells the model we want to fit a random intercept for each site. That is, we're allowing the mean life OE ratio to vary from one site to another. We should always include a random intercept in any model that we build that's based on data from several different monitoring locations. It accounts for the hierarchical structure to our data and means that we avoid the potential trap of pseudo-replication, which can give inflated type 1 errors or false positive results. The diagram on the screen here is a quick illustration really of the model that we are fitting. We have a single global slope effect, so we have a global intercept and slope represented by the blue dashed line. But then we also then allowing for each site, we're allowing the intercept to vary randomly from one site to another. So we're estimating a global intercept and slope coefficient, and we're also estimating how much variability there is among the intercepts from one site to another, and that's represented by this variance term, or sigma. When we fit a model, we also need to tell the function which data set to use. So here we're using a calibration data set called HE data. And you'll notice there's also a final argument at the end there, which tells the model whether we want to fit the model to the data using maximum likelihood or restricted maximum likelihood. If we set REML equals false, then we get unbiased estimates of the fixed coefficients. And if we set it to true, then we get unbiased estimates of the random variances. This might seem a little bit odd, but the model fitting process essentially works as a two-step process. We either estimate the fixed effects first and then the random variances as a second step, or vice versa. Typically, it's the fixed effects which we are more interested in. We want to understand the strength or the slope of the relationship between our biological metric and one or more hydrological variables. However, if it's actually the variability that you're more interested in, then you should set REML equals true. Those two methods, maximum likelihood and restricted maximum likelihood, actually produce very similar models if you're analysing a large data set. But for smaller data sets, the two approaches will diverge slightly. You will always get exactly the same fitted values from your model. But for smaller data sets in particular, you will find that the fixed coefficient estimates and their p-values and the random variances will vary depending upon the choice of setting. Although this is a very simple model, it's worth remembering that you can have any number of fixed predictor variables, and those can be continuous or categorical. So, for example, as well as having a Q95Z statistic, we could have any number of other flow statistics as well, as long as they're not too strongly correlated. We could also have a season factor, for example, a year factor, a regional factor, water quality statistics. The list is endless. This modelling approach gives us a lot of flexibility, as long as our data set is large enough to build more complex models that can disentangle the effect of different variables. When we fit the model, we assign the results to a model object, which here we've called that model 1. In this second example, we're doing exactly the same thing, but now rather than fitting a model with random intercepts only, we're fitting a slightly more sophisticated model which has both random intercepts and random slopes. We're calling this model 2. The only difference from model 1 is that now the random part of the model, the part in brackets and highlighted in bold, has the flow variable, the Q95Z statistic, within that random part. So now we are telling the model we want to fit a random slope. We want the effect of this flow variable to be not only a fixed effect, that's common to all sites, but also to allow that to vary randomly from one site to another. This provides a mechanism for exploring how consistently or otherwise that hydroecological relationship applies from one site to another. Implicit within this is that there's also a random intercept as well, but we don't need to specify that using a 1, it's produced implicitly. You can see from the diagram on the screen here how this kind of model gives us, again, a common fixed relationship for all sites. That's the blue dashed line. But now that line can fluctuate or vary not only in its intercept, but also in its slope. And that gives us a separate regression line for each site in our dataset. When we're modelling data of this kind, it's often of interest to include a random slope or 2 if we can, as this helps to control for false positive results. We just have to be aware that if we're building more complex models like this, then we also need a larger data set to be able to calibrate that model properly. And it's often the size of a data set which is the major limiting factor on how complex our model can be. That is, how many different predictor variables and random slopes it can accommodate. Having fitted a model to the data, then the next step is to use the summary command to view the outputs from that model. In this particular example on the slide here, I'm fitting a slightly more complicated model. You can see that now we have 2 different flow statistics, a Q95 term representing low flow effects and a Q10 term representing high flows. And both of those flow statistics also appear in the random part of our model. So the effect of both of those terms can vary from one site to the next. Also, for the purposes of illustration, I've specified to use the LMER function from the LMER test package. As you'll see from the output below, that gives us not only coefficient estimates for our fixed effects, but also approximate p-values. We're then using the summary command and applying that to the model output object, which produces the output that you can see on screen here. Now, there's quite a lot of information here, so we're going to look at it a little bit at a time, and just talk through what it tells us. At the top of the output, it first of all confirms the model formula that we've used to produce the model and the dataset that we've used to calibrate it. We then have some residual statistics, and then the two main bits that we focus on are the two tables towards the bottom of the slide. Let's start at the bottom by first of all looking at the fixed effects part of the summary output. This is in fact very similar to the output you get from any linear regression model. We have a set of coefficient estimates. We have a overall global intercept. We have a global slope for the Q95 effect. That describes the strength of the effect of that variable on our life OE ratios. And similarly, we have a slope coefficient for our Q10 variable as well, which describes the effect of high flow. Each of those coefficients has a standard error, which is essentially a margin of error, describing the degree of confidence or uncertainty attached to those coefficient estimates, the degrees of freedom, and a t-value, which ultimately give us a p-value. The number of asterisks is a quick indicator as to the degree of statistical significance. I would just stress again, however, that these p-values are approximate. Mixed effects models are quite complex in the way that the models are fitted to the data, and these p-values use a fairly simple method to provide an indication about the likely statistical significance of each coefficient. If you're really interested in getting p-values, there are some more slightly more robust methods that you can use, such as likelihood profiling and bootstrapping. However, both of those techniques are beyond the scope of today's workshop. It can be quite useful to visualize those relationships using partial effects plots. Partial effects plots show the modelled effect of each predictor variable when all the other predictors are held constant at their mean values. Here we're focusing on the fixed effects only. So this is the effect of the flow variables, which is common to all of the sites in our data set. If you look at the small table at the top of the slide here, I've just highlighted the intercept and the two slopes for our two different flow variables. We can then use the plot model function from a package called sjplot to visualize those relationships. We take our calibrated, our fitted model, which in this case is mod 3. We set type equals pred. That means that the predictions is generating predictions from the model to illustrate the effect of each variable in turn. And pred.type is set to FE because we want to focus only on the fixed effects. If we've got two or more fixed effects in our model, then we can set grid equals true to plot those up side by side, as you can see on the screen. This particular model is a special case in the sense that we have two flow variables, both of which are standardized. So they take a mean value of 0, and 0 represents the flow conditions which are normal for that site. Hence, when we then use the plot model function, that shows us how the life OE ratio changes as each of those flow variables alters, whilst holding the other variables constant at their mean values. It also means that the intercept in our model, 0.999 in this example, describes the expected life OE ratio when the flow conditions are at normal levels for each site. If you compare the two plots side by side, you can see that the global slope is much steeper for the Q95 effect than it is for the Q10 effect. The slope for the Q95 effect is 0.0134, so it's a relatively strong relationship, and you can also see from the grey shaded lines that that's quite a strong, significant relationship. And by contrast, the Q10 effect, the coefficient is actually quite close to 0, and the confidence intervals are relatively wide. So we can't be sure whether that Q10 effect is significantly different from 0. Visualizing the data in this way is a very useful technique for exploring exactly how much change in the response variable we can expect between very low and very high values of each flow predictor. Going back to our summary output, we can also extract from this information about the strength of the random effects in the model. These random effects are represented as variances. The higher the variance, the greater the variability in the intercept or the slope from site to site. The red box shows the part of the summary output which describes these random effects. In this model, we have three random terms. We have a random intercept, describing how much the life-OE ratio varies on average from site to site. We then have two further variances which describe the degree of consistency or variability in each of those flow effects across our sites. Finally, we also have a residual variance at the bottom of this table. That describes the amount of unexplained variation in our data set. That is the variation in our life-OE ratios from one sample to another, which we can't explain in terms of flow. You'll notice that this output also confirms the total number of observations in our calibration dataset, which in this case is 929, and also the number of unique levels in our grouping factor. In this case, we have 36 different sites. It's really important to keep an eye on these two bits of information at the bottom of the output there, because it's very easy to lose data along the way when you're processing it. Data can fall out because it doesn't join properly, or you may have missing values as well, which result in bits of data falling out of the calibration data set. Again, it can be useful to visualize these random effects, and again we can call on the plot model function from the sjplot package to help us. These plots are called caterpillar plots, and they visualize the random intercepts and slopes for each of the 36 sites in our dataset, and it plots those as deviations from the global coefficients. This allows us to see which individual sites have higher or lower intercepts, or steeper or less steep slope effects. You can see on the left-hand side here that this time, when we use the plot model function, we set type equals RE, because we want to focus on the random effects. We can also adjust the scale at the bottom of the plot there using the ylim function. If we refer back to the output from the summary, we can see that the largest of the three variances is the variance associated with the intercepts. That's telling us there's a lot of spatial variation in our biological metric from one site to another. And you can see that also in the plot. You can see that the points describing the intercepts of each individual site fluctuate. They vary quite a lot from one site to another, so we have a relatively high variance. The points in blue pick out those sites where the intercept is random intercept is greater than 0. So these sites have a higher than normal life-OE ratio compared to the other sites in the data set. And conversely, the red points pick out the sites with lower than usual life-OE ratios. Similarly, we also can visualize the variation in the Q10 slopes and in the Q95 slopes across our 36 sites. The Q10 variance is the smallest of the lot, and again you can see that in the caterpillar plot. There's not a lot of variation or scatter across those 36 sites, and that's not particularly surprising given that the global fixed effect for Q10 was very weak, so there doesn't appear to be much effect of high flows on our life scores in this particular data set. The Q95 effect had a stronger overall global effect, and there's also evidence of a moderate amount of variability in the strength of that hydro-ecological relationship from one site to another. Now, you might remember from one of the earlier tutorials that mixed effects models actually give us a hybrid. They provide a fixed effect which describes the global or common effect of a flow variable across all of our sites, but then that's blended with the site-specific data that we have available for each sampling location. And what we end up with is the fixed effect plus the random effect, and that gives us a mixed effects estimate of the intercept and the slope for each site. Again, those mixed effects estimates can be extracted fairly readily from our model using the coef function. So we apply the coef function to extract the coefficients from our model, and the double square brackets just extracts the first element of that list, which gives us the intercept and the two slopes for each of the 36 sites in our data set. With a little bit of very simple data manipulation, we can then feed that table of coefficients into a ggplot, and that produces the diagram shown on the right-hand side of the slide. Here, for each of the 36 sites, we are now plotting up the slope coefficient that describes the effective Q95 on our life OE ratios. Sites with points over to the right-hand side indicate a large positive slope, that's a strong positive effect, and points over towards the left indicate a weaker effect. The global effect, 0.0134, which is our overall fixed effect, represents the middle of our data set. So that's the strength of the slope for a typical site in our data set. And you can see that some sites have a steeper slope than that, and other sites have a slightly weaker slope. What's particularly telling is that in this particular example, out of the 36 sites on our data set, 35 have a positive slope. There's just one site here where the slope coefficient slips slightly into negative territory, suggesting that higher Q95s are associated with lower life scores. But overwhelmingly, the evidence is that higher flows are associated with higher life scores, which is what we would expect. When you're fitting linear mixed effects models using the LMER function, you may encounter warning messages from time to time advising you that your model is singular. Singularity occurs when we have an overfitted model. That is, we have a model which is too complex for the amount of data that we have in our calibration dataset. As well as getting singularity warning, another thing to watch out for that indicates this problem is the correlations for our random effects. These describe how correlated the intercepts and the slopes are in the random part of our model. If those coefficients become perfectly correlated and take values close to +1 or -1, that's an indicator that we may be overfitting the data. Also, we may see that some of our random variances are estimated as being very close to 0. That too is an indicator of singularity and model overfitting. So singularity basically means that our model fitting process is coming up against some constraints or some boundaries. Variances can never be negative, they can't be less than 0, and correlations between our random intercepts and slopes can never be more than +1 or -1. In this particular example, we can see that there's a correlation of -0.96 between the random intercept and the Q95 term. Again, this is an indication that we're getting very close to an overfitting situation. This happens particularly in two different situations. Either we have a relatively small number of levels of our random grouping factor, so that is, we have relatively few distinct sites in our data set. And as an absolute minimum, we would need 5 sites to be able to have any hope of estimating these random variances with any accuracy. Ideally, we would like many more sites than that, typically 10, 20 or more. Alternatively, it may be that our model is just simply too complex. If we're fitting a model with several different random slopes, for example, and that those random terms have lots of different levels, that too can create singularity issues. Now, if you run into this problem, then there's several different ways around it. You can use different model fitting algorithms, some of which are more robust to this problem. You can use entirely different regression modelling approaches altogether. But if you want to stick with the linear mixed effects models as we've talked about them in this tutorial, then the simplest and most straightforward course of action is to simplify your model back a bit. So in this particular example, we might choose, for example, to drop at least one of the random slope effects from our model formula. The Q10 effect seemed to be non-significant, having a very weak effect. So we could drop it as a random slope, and we could also potentially consider dropping it as a fixed effect as well. Simplifying the model in this way is a surefire way of resolving these singularity issues and ensuring that we have a model which provides us with robust and credible coefficient estimates. If you would like to have a go at using these functions to calibrate some predictive models, then we've set up some example datasets and code over on the POSIT Cloud account, which you can access by following the link that accompanies this video. Look for practical exercise 2, and within that R script you will find some example code that you can run and inspect the output.